That right there, that's R, isn't it? I'm only labeling it because my formula has it in there, right? Yes?
I think I know.
Okay, what do you think?
So you could write R in relation to H, like you convert R to H because the shape of the cone that you're creating with the water is identical to the shape of the cone that holds the water. So you would take like just the same exact thing that we did with the triangle, the relation of the one side or the height over the length, you would do that for this.
So there's some like proportional relationship between what's going on with the water and the cone. You have a cone in a cone, right? So I think the easiest way to see that's correct, but the easiest way to see this, I think, is to imagine like everything is frozen, okay? The water's frozen, everything's frozen, and just imagine cutting the cone in half, all right? Just come through with a sword and just cut it in half and open it up and look at it, a cross section of it. Right down the middle of the cone, cut it, open it up, and here's what you'd see. All right? You would see a big triangle, and then you would see a small triangle, right? That's what you would have. And now if we look right down the middle, just drop a line straight down the middle like this. What we've created, do you see on the right-hand side or left? We can do either side, but let's just do the right-hand side. Do you see that we've created that same picture with the man and the light pole? It's just turned over sideways. Let's see if we can label that. I'm going to keep going. I'm going to do it. I don't know where to do it. Right here. So take that picture. Just look at the right side. Here's the water level. Water height. I can label this R, and I can label this H, right? Can you label this? What is this?
6 or 3.
3, that's 3, right? And then what's this from here to here? 4. That never changes, right? Because that's the big cone. Now I'm going to go a step further. I'm going to draw both of those triangles separately so you can really see them. So there's my big triangle. I'll do the small triangle in blue. R, H, 3, 4. This has a right angle, that has a right angle. This angle and this angle are the same, right? Because they both come from the bottom of the cone. And these two obviously have to be, well, they have to be the same if the other two are the same, right? What did you say?
You know H is 3.
I know H is 3. Not yet. Not yet. Not until after we get the equation, after we differentiate it. Okay? What this will allow us to do, though, is set up a relationship between R and H. Remember our goal here. Our goal is to eliminate H, right? To eliminate R. That's our goal, to somehow get this R out of here. And so what I'm going to do is I'm going to use this geometry to create a relationship between R and H. And then what I'm going to do with that is I'm going to somehow replace this R, and it's going to be in terms of H instead. So what can I do? 3 over 4, I could do those two as a proportion. 3 over 4 must be R over H. I believe that. Yeah? Yeah, everyone agree? We could do that. There's a bunch we could do, but we could do that. And I'm going to take that and solve it for R. So I'm going to multiply both sides of this equation by H. Do I need to state that this is similar? You understand these are similar triangles, right? Okay, so we have this. Multiply both sides by H, we get 3/4 H equals R. And this is what the reason I solve for R is because I can replace that R now with this, can't I? So here I go. Here's my equation. My equation is volume equals 1/3 pi, now R squared, right? R squared. But R is this, 3/4 H. So this is 3/4 H squared. Now don't forget, that's just R squared. You still have times H, don't you? You have another H out here. Do y'all see that we now have an equation that has just V and H in it? And now if we differentiate that, we're going to get a dV dt and we're going to get a dH dt, and then we'll be in business. All right, before I differentiate, let me clean it up. I'm going to square this. When you square this, you have to square the fraction and the h. So this is volume equals 1/3 pi. Square 3, I get 9. Square 4, I get 16. Square h, I get h squared. And then I still have an h there. Cleaning up. Volume equals 3 over 16 pi h to the 3rd power. That is the cleanest volume formula that I can get. So what we're saying is for this cup, right? This 6-inch wide cup by 4-inch tall cup, if you have water in here, the volume of that water will be 3/16 pi times whatever the height of the water is cubed. We have generated that formula off of the geometry of this cup. And now we can differentiate it. We good? Cross section. Similar triangles. Eliminate the variable. I promised fun, I'm delivering fun. Derivative. What's the derivative left side? dv dt. Happy to see that. I know that's 2 pi, don't I? dv dt. Okay, equals. All a constant, right? That's all a constant, so it's going to come for the ride, 3/16 pi. Now the derivative of h cubed. 3h squared times, we don't want to forget that, right? dH dt. We would know, if we forgot that, we would know we have a problem because that's what we're trying to solve for and it wouldn't be in our equation, right? So happy. I think I'm happy about all of this. I don't need to even solve for anything else, right? Because dv dt is given to me and I know h. See, now I can go back over here. Now I can go here at the instant in time when h was 3. I can plug 3 in for h and I've got this. So dv dt. No, sorry, we know dv dt. dv dt is 2 pi. Sorry, 2 pi equals 3/16 pi times 3, okay, times h, which was 3 again, squared times dH dt. Real quick, I see pi's on both sides, right? I'm just going to divide by pi. That'll just kill the pi's off. On the right, I think I have 81 over 16. Yep. Yeah, 81 over 16. So 2 equals 81 over 16 times dH dt, right? 3 times 3 times 3 times 3, right? And then just flip whatever, 32 over 81. Yep. Does that reduce? I don't know if it reduces. 32 over 81. I tell you what, give me that as a decimal. Please, somebody. 0.4. 0.4? Oh, so exactly?
Approximately.
Oh, approximately, okay. 0.4, 0.4 approximately. dH dt. How do we measure that rate of change? H is height. Height's measured in inches, so inches per time was measured here. Seconds, inches per second. So 0.4 inches per second. So if you have a conical cup that's 4 inches tall, 6 inches wide at the top, you start pouring beer in there at 2 pi cubic inches per second. Exactly the moment the beer is 3 inches high in the cup, it's coming up the edge of the cup at exactly, approximately 0.4 inches per second. Almost half an inch per second is how fast it's coming up the edge. Let's take a look at an animation. What in the hell's going on? That's my code, yeah. I have to type all that up to make this animation happen. That's the code I had to write. It's too big. Hopefully they'll do it. This is weird. The projector's weird. Let me try something real quick. There, if I make that a little smaller, this might work. Maybe not. There, and see in the beginning how fast it's coming up? And then as time goes on, it's just slow, it slows down how fast it's coming up. Watch in the beginning here. It's when it starts over. Watch how fast it comes up in the beginning. See how fast that came up? And then now just from here on just continues to slow down. So if I said, if I asked, hey, how fast is this water coming up, right? How fast is this level rising? When it's half an inch from the top, right? Instead of 1 inch, half an inch from the top. We should expect a number bigger or smaller than that? Smaller, right? It should be moving slower as we get higher. All right, we've done how many problems today? 3? We're doing good. The runner problem. The thing about these problems, I think, that really causes issues, other than the fact that they're word problems, is that no two problems are the same, right? So it's not like when you learn the product rule, you start to understand, okay, product rule is this, derivative, derivative first one time. Second, it's not mechanical. Like you have to really kind of extract the math from the problem, right? So I know that's a challenge. You only get good at this by practicing. And I was having a conversation with one of your classmates the other day. When it comes down to it, problem solving is why we're here, okay? This is not about, calculus is not about, you in the real world ever doing a related rate problem. This is about you in the real world being a problem solver, being a critical thinker. You're all STEM majors, whether it be biology, computer science, engineering. At some point you want to be able to solve problems. And problem solvers don't like curl up in a ball in the fetal position when they get stuck. They basically do the opposite. They can't sleep until they figure it out. Like the problem possesses them. And that's what I think problem solvers are. Like that's the way I guess I've always been. Like sometimes I stay up when I have a problem that I'm trying to solve. It'll keep me up all night, right? So getting to that point where you're confident just comes with time. You have to just continue to just be persistent, right? I'm going to give you all a minute to try and just draw this out. At least try and draw yourself, either the general or the instant. Why don't I give y'all like 5 minutes? Let's see if y'all can come up with anything on this. You can talk to each other, that's fine. I'm not going to grade this. Just want to see what you can come up with, all right? And I'm going to step out for just a moment. I hope you have at least something like that. Circle with a radius of 50 meters. A person, a friend, is watching them run around the track. The person is 100 meters from the center of the track. This person could be anywhere around here, right? I just put them directly to the side. I could have put them directly straight up. Did anyone go straight up? Yeah, it doesn't matter where they are. Is this person running clockwise or counterclockwise? Doesn't say, doesn't matter, okay? So I'm just gonna make it counterclockwise only because in pre-cal we did all our angles counterclockwise, so let's just do that. I'm gonna make this person be in motion like this, right? Like that, moving around the track like this. How fast is the distance between the two changing when they're exactly 120 meters apart? So that's the instant in time. I have this. From here to here, we know that's 100. And then 120 meters would be, I don't know, the person would either be here on the top or maybe on the bottom, but this right here, the distance there is 120. And we know that this distance here to here is 50. You'll see that picture?
So that instantaneous rate of change is going to be identical whether she's moving closer towards her or away from her at that moment?
That's right. Whatever answer we get, we don't know if she's moving away or towards. But it's going to be, we're going to look at it almost like an absolute value, and we'll just be like, that's the rate of change.
Gotcha.
Yes?
Oh, because there would be two answers, right?
Yeah, that's what we're saying. We don't know which, if she's moving away or towards the person. When she's 120 meters apart, it could be in two different scenarios, right? It could be when she's moving away or when she's moving towards. We don't know which one it is. The way I've drawn it, she's moving away, right? The way I've drawn this, she's moving away because she's going like this. Is it she? I did say she. She runs, okay. Okay, there we go. Yes? What am I given? What am I given? I have a speed, don't I? 7 meters per second, right? That's d something dt. But what is it? Like in my general picture, can I label that 7 meters per second? Like with the man walking with the shadow, it was his distance from him to the pole, or to the pole, right? That was x. And we said it was dx dt. Can we do that here? Or if we can't, why can't we?
Okay, it's because there's no reference point? There's no origin?
It's a circle, right? It's not a straight line. We can't draw a straight line distance and say it's changing at 7 feet per second, or 7 meters per second, right?
The diameter, then take the circumference and divide by 7 or something?
If we take the circumference and divide by 7, what would that give you, though?
It would give you 2 pi r, which is 100 pi divided by 7.
What would that give you?
The rate that she's going around the circle?
No, we know the rate that she's going around the circle. She's going at 7 meters per second. You're getting something, but what is it?
Arc length?
No, because the circumference. Okay, let's just make this simple. What if the distance
How
around?
long it takes her to get around the circle?
That would be how long it takes her to get around the circle. Okay, so let me go through that. Let's say that the distance around this, let's just say for the sake of making it easy, let's say the distance around this, the circumference was 100 meters. And she was running at 10 meters per second. How long would it take her to go around the circle? 10 seconds, right? You take the circumference and divide it by her speed, and that's going to give you how much time it takes her. So we could do that. Do we need it? I don't know, but that's what that calculation would get you, right? Man. Okay, let me draw something else. We can label this at least, because this is, I don't know what to do with that yet, right? So I'm going to label this to here, right? I'm going to call that, I don't know, I'm going to call it capital F for friend, okay? That's the distance to her friend. I do want to know how fast that distance is changing, right? That I think I can put on what I want. I want df dt, right? And I want that at what moment? When f is 120. So I know what I want, and I know when I want it. What I don't have is this, so that I can connect two variables together. I don't have that, right?
You know the furthest away she can be is 150.
I do know the furthest she can be away is 150, yes.
Yeah.
Mm-hmm. But I need a variable here so that I can connect an equation, right? I've got 13 minutes to figure out a variable here.
So why can't you just choose an arbitrary letter and just say that that's how fast she's going around the circle?
Okay, so give me the letter you want me to use.
I guess, well, S.
S?
5.
Hmm?
I said S looks like a 5.
Okay, yeah, my S's did look like. Let's go with X.
X.
Okay, let's just go with X to make it simple. So if I say that this is dx dt, where's X in the picture? Where? You can't, though. It's not a straight line. When you say 7 meters per second, that's a straight line distance. Well, let me put it this way. What this actually is her linear speed. All right, that's her linear speed. That's if she was running in a straight line, that's how fast she's going. But see, she's not running in a straight line, she's running around a curve. But she is running at 7 meters per second, right? Yes? Okay.
Could that be like, is the trick you have to convert this to like cosine or sine?
Well, maybe. I mean, maybe. We know her linear speed, right? From the linear speed, we can actually get the angular speed. This is the key to the problem, all right? Knowing how fast she's running around can tell me how fast the angle is changing, right? Because as she runs around, if I'm standing in the center of the circle, if I'm watching her from the center of the circle, right? Then this is always the same for me, isn't it?
Yeah.
That's called angular speed. I'm going to get dizzy, right? So how do we go from her linear speed to an angular speed? This is pre-cal. Yeah, this is pre-cal. Wasn't that a class you're supposed to take before this class? Oh yeah, that was a class you take before this. But we do it usually in pre-cal right in the beginning of the semester, so you forget about it. And I don't want us to be thinking about formulas. Oh, there was this formula. It was like omega, blah, blah, blah. I just want us to try and figure out, can you tell me how fast the angle is changing? All right, so let's not overcomplicate this. Let's think about the distance around this circle. What's the distance around this circle? What's the distance? So from here, if she goes around one time, right? That's circumference, and that's going to be 2 pi times the radius of the circle, which is 50, right? So the circumference of this is 100 pi. Agreed?
Yes.
All right. She's got to cover 100 pi meters, right? That's how many meters it is around? Okay. She's running how fast? 7 meters per second, right? So how much time will it take her to go around?
5 by 7.
We take 100 pi, the distance, right, and divide it by her speed, which is 7 meters. Divide this by 7 meters per second, and let's just leave that as an exact number. It's 100 pi over 7 seconds. This is exactly what you were just saying a second ago, right? If the distance around it was 100 meters, and she's running at 10 meters a second, it would take her 10 seconds. If the distance around was 200 meters, and she ran at 10 meters per second, it would take her 20 seconds. If the distance around is 100 pi meters, and she runs at 7 meters per second, then it's going to take her 100 pi divided by 7 seconds. Yes?
Then take 360, divide by that.
Now, yes, so the time, this is how much time it takes her to go around once, right? So in terms of an angular speed, how long does it take me to go around once? that same time, right? So I go through 2 pi, I'm not going to use degrees. I go through 2 pi in that much time. So the angular speed is going to be the distance I travel over the time it takes me. What was the distance I travel? The angular speed, hold on. When I say distance, I'm talking about the distance, the angle. What's the change in the angle? You go 2 pi, and you do that in how much time? This much time. So divide that by 100 pi over 7. And that's the same as 2 pi times 7 over 100 pi. The pi's cancel, and you should get 14 over 100, which is 7 over 50. 7 over 50 is your angular speed. I know this is confusing. This is one of the hardest problems, okay, because this is messy. So I'm going to use the linear speed. I'm going to get rid of linear speed. And what I'm going to do is I'm going to come over to this picture, and I'm going to label in here the angle theta. So imagine I'm measuring theta here. I can measure how fast theta is changing, right? How fast is theta changing? Well, that's what that is. That's what the angular speed is. So this 7 over 50 is d theta dt. 7 over 50? Radians per second. I know this is tricky, all right? Because we're taking the linear speed of the runner around the track and converting the linear speed into an angular speed. And we only have 6 minutes. I'm not going to be able to finish this problem, but you're going to try and finish it. How about the equation? Look at the picture. Can you connect F and what together? Theta. I need an equation that connects F and theta.
The sine rules, the sine relations, where it's like sine of theta over.
Law of sines?
Yeah.
Not quite. So you're thinking law of sines. First of all, everyone, this is not a right triangle. So you can't use sine, cosine, tangent. You can't use like SOHCAHTOA, opposite over hypotenuse. You can't do any of that because this is not a right triangle, right? This is just an arbitrary triangle. As she runs around that triangle, changes shapes. Changes shape, right? It's not right? There are certain times when it is a right triangle, right? When she's straight up, it's a right triangle. When she's straight down, it's a right triangle. But any other place, it's not a right triangle. So if I want a relationship between F and theta, I need something from pre-cal that connects the side of a triangle, the sides of a triangle to the angle inside. Law of sines works if you have 2 of the angles. If you have 2 angles and 2 sides, you can use law of sines. But I don't have 2 angles. I only have 1 angle and I have 3 sides. So that's law of cosines. All right, so yeah, what the hell is law of cosines? So go back to your pre-cal notes, I don't know, somewhere in there. It's this: if you have an arbitrary triangle, and we call, let's say, this angle A, B, and C, this is little a, little b, little c. The law of cosines says, anyone remember the law of cosines? It's on your formula sheets. Okay, so there's 3 of them, aren't there? Just read the first one to me.
A squared.
Okay, a squared equals.
B squared plus C squared minus 2BC cosine of A.
There are 3 of these, but they're all basically the same formula. It says, if you want to know one of the sides, A, you need to know what the B is, the C is, the B and the C, and you need to know the angle, capital A. So in order for me to figure out, like if I wanted to find out what this was, A, I would need to know what B is, I would need to know what C is, and I would need to know that angle. If I had that, then I could find the relationship. Here, I could set up that equation using this, right? So I'm going to use that. This is like the little a, right? This is like the little a. This is capital A. This is B. This is C. So my equation is going to be what? What are we saying this one was? Well, let me say it. I want this and this. The angle here and the side opposite, that's little a, that's big A. So for us, I want this to be little a, big A, like that. Little a, big A, and then this is B and C. All right? So using this formula right here, we would have what for us?
120 squared.
Where are y'all getting 120 from?
F squared.
This is the parameter.
Yeah, it's gonna be F.
F.
The little a.
I'm gonna hit somebody. Did you just fix 120? Did you just fix F? You can't fix F yet.
Give the implicit, yeah.
Not till the implicit, right? I'm just trying to make a point, like exaggerate it. I'm not gonna hit you.
We have it on video.
You have it on video. I'm not gonna hit you, I'm sorry. Okay, so I know you wanna put 120 here later, okay? Right now, it's F, right? It's F squared equals, okay, now